Okay, so now we're going to do a problem that combines a lot of information from the last couple chapters together. Okay, and so the first thing I want to point out is that if you look at PowerPoint 4, right, slide 1, right, and slides 3 through 5 will have cartoons that are associated with the last video that we just watched. So go and pull those up. Make sure you can kind of see what's happening. The first slide shows like the formation of a solid through just pouring two different solutions together, okay? And then slides 3 through 5 will deal with this example problem that we're going to do, which is also, though, like the same sort of concept. Essentially, what this example problem asks us to do is to take a solution of silver nitrate, and because you're given it's a solution, you know it's aqueous, right? And also react it with a solution of sodium chromate, which is aqueous. Now, just as a little quick review on our solubility rules, why would this be aqueous? Well, nitrates are aqueous. And is silver one of the exceptions? No. Why would this be aqueous? Well, group 1A metals are aqueous. Is chromate an exception? No. So this will be aqueous, this will be aqueous because they fit categories on our solubility chart. All right. Even though this is on the slides, I still want to walk through the idea. What do we do to predict the products here for this? Because we're not just reacting a solution with this solution, we have very specifics, very specific information about those solutions. We know a certain volume and molarity of this solution and a certain volume and molarity of this solution. So actually, we're going to be able to make some predictions, and the prediction we're going to make is the mass of solid that forms, if any solid forms, if there is a precipitate at all. So let's figure that out. Find our positive things and switch them. Ag must be a +1 charge because it's attached to an NO3. So chromate is CrO4 minus 2. So how many Ags need to attach to it? 2. Ag2, CrO4. And I can consult my solubility rules to see if a solid forms. Okay. Next, all right, the Na can attach to the NO3 when I pour these guys together, okay? If I take the positive things and switch them. Well, does it take two NAs to balance the charge of an NO3? No. All right, Na is plus, NO3 is minus, put them together, and you get NaNO3, okay? I can look at the solubility rules to determine that state. Let's balance first, okay? Well, I need two Ags here, so I'm going to put a 2 here. Ooh, and then I have 2 nitrates, right? And I have 2 sodium. Okay, so I'll put a 2 here. Okay, and then I'm set. So did you notice how I balanced that? It's another important thing I just want to talk about as a quick little aside. Notice that oxygen is found in chromate and in nitrate, but chromate shows up on this side of the reaction as a whole chunk, and nitrate shows up on this side of the reaction as a whole chunk. So don't balance nitrogens separated from oxygen, balance nitrates. So here there's 2 nitrates, and here there's 2 nitrates, so I know I'm balanced. Here there's 1 chromate, and here there's 1 chromate, so I know I'm balanced. Now I can consult my solubility rules. Let's do the easy one first. This is a group 1A metal, this is a nitrate. For both those reasons, only though we only need 1, we know that that's aqueous, right? We look at our chart for chromate. We don't see it. We look for silver. Silver is only in reference to things that aren't chromate. So silver 1 chromate does not fit our chart anywhere, right? So that means it is a solid. Now for practice, let's write a total ionic equation and a net ionic equation, even though we don't really need it, okay? So we can go ahead and we can tackle this problem as is right now, but just for practice, let's get a total and a net. Remember how to get a total ionic reaction? We take all the aqueous species and we break them down into their component ions. So this breaks into 2 Ag pluses. Why do we get 2 of that? Oh yeah, the stoichiometric coefficient translates both here and here. If we have 2 AgNO3s, we get 2 Ag pluses and we get 2 NO3 minuses. Okay? When this breaks down, this aqueous species, we get 2 Na pluses that float far away from each other by themselves. And we get a CrO4 minus 2, which is also aqueous. On the product side, we don't break down the solid. And the sodium nitrate breaks into 2 Na pluses and 2 NO3 minuses, each of which are aqueous. And so now we try to identify the spectator ions. Sodium hasn't changed and neither has nitrate, so we can cancel those guys out. And we see that the final net ionic reaction is 2Ag plus a chromate gives your silver 1 chromate precipitate result. And you'll see all this summarized pictorially on slides 3 through 5. But again, I just wanted to go over it verbally one more time because it is a really important concept, and seeing another example is, just reinforcing those ideas again. Now let's get to the crux of this problem. We have a prediction to make. We're given information about this reactant. We're given information about this reactant. We're asked to make a prediction. What kind of problem does that sound like? That fits exactly our categorization of a limiting reactant problem. And that's what this is, okay? Do I have a balanced full molecular equation that I can use here? Absolutely, all right? So I can build mole-to-mole bridges, and I can follow that limiting reactant process to the T with the information that's given, right? So let's do that together. How do we do limiting reactants? We take this reactant information, make it product information. Because we're asked to make a prediction about the solid, let's take this information and make it solid information. Then we do the same thing for the other reactant. Let's take this information and make it solid information. And then which one do we pick that decides which is the mass of the solid? We circle and we pick the smaller amount. So here's what the math for this problem looks like. Again, I'm just kind of showing you how you can combine up all these ideas into one comprehensive example. We have 2.00 liters of our AgNO3 solution. I know the molarity, and I also know that molarity translates into moles per liter. So it was 2.0 moles of AgNO3 for every 1 liter of solution. I have a balanced chemical reaction. That tells me for every 2 moles of AgNO3, using the stoichiometric coefficient, I have 1 mole of my precipitate, Ag2CrO4. And because the problem asked me for mass, I can look up the molar mass of Ag2CrO4. 395.8 grams of AgCrO4 are in 1 mole of Ag2CrO4. And I plug this in my calculator and I get 791.6 grams of my solid Ag2CrO4. I already mentioned this, but we're not done. Even with this step, we're not done. We should check significant figures, and hopefully you could see that there would be 2 significant figures. Before a limiting reactant problem, I don't just do one of these conversions. Am I given another bit of information to use? Absolutely. You're given information about the other reactant. And that other reactant had 5.00 liters of solution as its starting point. Its molarity was different, all right? We have 0.50 big M. What does big M translate into? Moles of Na2CrO4 per 1 liter of solution. Big M translates into moles per liter. Okay. Now I can use my stoichiometric coefficients for my balanced reaction. For every 1 mole of Na2CrO4, we have 1 mole of our solid precipitate, Ag2CrO4. And then finally, we can finish it off, right, with our molar mass, which is 395.8, right, grams of Ag2CrO4 for every 1 mole of Ag2CrO4, right? We can plug this in our calculator, right, and we get 989.5 grams of Ag2CrO4. And I just want to point out significant figures, and then just as a quick review, remind you, right? can I compare 2 liters of 2 mol? Oh, sorry. Yeah, can I compare 2 liters of 2 molar AgNO3 to 5 liters of zero point 0.5 molar Na2CrO4? Well, no, those are completely different objects. But can I compare 791.6 grams of Ag2CrO4 to 989.5 grams of Ag2CrO4? Yes, absolutely, I can compare these because they have the same number and, or sorry, unit and identity. They have the same unit and identity. And so how much is made? Well, these numbers tell us that the maximum amount that this species could make, this reactant could make, is this. And the maximum amount that this species could make is this. So what species is made, right? What species runs out? How much precipitate actually is formed? The smaller amount. That tells me that AgNO3 is the limiting reactant, and that tells me that Na2CrO4 is the reactant in excess. So how would you answer this question? You would answer it as 790 grams of Ag2CrO4 solid as the amount of precipitate that forms. Okay? So this was a nice little review of 2 different concepts, right? Doing double replacement reactions in the concept of in the context of precipitates, predicting a precipitate will form, writing total and net ionic reactions just for practice, and then we can run through a limiting reactant process just in the same way we did before, now in the context of this solution aqueous environment chemistry. We have one last video that kind of follows along these same lines next time, and the next video deals with acid and base neutralizations, and we kind of do the same sort of idea, but we switch it up slightly, and it makes the calculations a bit easier because next time we're going to refer to a very specific experimental technique called titrations.